Picture one of the most hostile environments on Earth, the Andean Altiplano, where the Atacama Desert receives less rainfall than the Sahara, where oxygen is thin enough to cause altitude sickness, and where temperatures swing from freezing nights to scorching days. This is not a place where civilization should thrive. This is a place where survival itself seems questionable. Yet, against all environmental logic, ancient Andean civilizations like the Tiwanaku, Wari, and Inca didn't just survive here. They built sprawling agricultural empires supporting hundreds of thousands of people. How? The answer isn't luck or primitive determination. It's engineering brilliance that would impress modern hydraulic specialists. When you look at the Andean landscape, you see an impossible contradiction. Glacial peaks rise above 20,000 feet, covered in ice and snow year-round. While just miles away, valleys and plains exist in extreme aridity, where rainfall is measured in millimeters per year rather than inches. The water is there, locked in ice at high altitude. But getting it to where crops could grow required solving an engineering problem that would challenge modern technology. These ancient civilizations needed to capture water at the source, transport it across miles of hostile terrain, prevent evaporation in intense sunlight, maintain consistent flow despite extreme elevation changes, and distribute it efficiently to agricultural zones. They accomplished all of this using stone tools, human labor, and a deep understanding of physics that wouldn't be formally documented in European textbooks for another 1,000 years. The first challenge was capturing glacial meltwater before it disappeared. At high altitudes, meltwater emerges from glaciers in small streams, but the arid air causes rapid evaporation. Ancient engineers constructed collection basins directly at glacial outlets, using precisely shaped stone channels to direct water immediately into protected systems. These weren't crude ditches. They were carefully engineered structures with specific angles calculated to maintain optimal flow velocity. Too slow, and sediment would accumulate, clogging the system. Too fast, and erosion would destroy the channels. The stone lining was critical. Desert soil in the Andes is extremely porous, meaning water seeps away rapidly through underground absorption. Early experiments with unlined channels would have resulted in massive water loss, making long-distance transport impossible. The solution was to line every channel with tightly fitted stones, often using multiple layers. The outer structural layer used large stones fitted together with remarkable precision. Some joints are so tight you cannot insert a knife blade between them. Behind this, engineers placed smaller stones and clay sealants to create a nearly waterproof barrier. But here's what separates ancient Andean engineering from simple craftsmanship. They understood hydraulic pressure. Water flowing downhill builds tremendous force, especially across elevation drops of thousands of feet. Modern concrete pipes can crack under such pressure. Ancient engineers designed expansion chambers, strategic points where channels widened, allowing water to slow and pressure to dissipate before continuing. They also built their systems to be earthquake-resistant, a critical consideration in one of the world's most seismically active regions. The fitted stone technique, without mortar, actually provided flexibility, allowing walls to shift during earthquakes without catastrophic failure. Perhaps the most ingenious aspect of Andean water management was the extensive use of underground aqueducts. While many civilizations built open channels, Andean engineers recognized a fundamental problem: evaporation. At high altitude, intense solar radiation and low humidity cause water to evaporate at shocking rates. An open channel exposed to full sun could lose up to 90% of its water over a long distance. The solution was to bury the water system. Archaeological surveys using ground-penetrating radar have revealed networks of subterranean aqueducts extending for miles, carved through solid rock or constructed using fitted stone tunnel techniques. These underground channels maintained cool, stable temperatures, virtually eliminating evaporation losses. But constructing them required solving an even harder problem: precise surveying. To maintain consistent water flow through an underground tunnel, engineers needed to establish and maintain an exact gradient, typically between 0.5 and 2 degrees of decline. Too steep, and water velocity would cause erosion. Too shallow, and flow would stagnate. Without modern laser levels or surveying equipment, how did they achieve this precision? Evidence suggests they used water-level instruments, essentially long channels filled with water that would naturally find a level surface, allowing them to establish horizontal reference points. From these, they could calculate exact gradients using marked poles and simple geometry. Remarkably, when modern engineers survey surviving aqueducts, they find gradient consistency maintained over miles with accuracy within fractions of a degree. Some of these structures, built between 600 and 1400 CE, are still functional in 2026, still delivering water with their original efficiency. The hydraulic systems weren't built in isolation. They existed specifically to enable large-scale agriculture on engineered terraces. These weren't simple hillside gardens. They were massive civil engineering projects transforming entire mountainsides into stepped agricultural platforms. Each terrace required sophisticated soil engineering. The Andean engineers created multi-layered terrace foundations, large stones at the base for stability and drainage, followed by layers of gravel, then a specific mixture of topsoil that retained moisture while preventing waterlogging. Water distribution on these terraces demonstrates advanced understanding of flow control. Stone gates and diversion channels allowed farmers to direct water to specific sections, effectively creating an ancient irrigation scheduling system. The terraces themselves created microclimates. The stone walls absorbed heat during the day and released it at night, moderating temperature extremes. The presence of water increased local humidity, creating growing conditions that shouldn't exist at 12,000 feet above sea level. The system was so effective that these civilizations grew multiple harvests per year of crops including potatoes, quinoa, maize, and various tubers. Agricultural productivity that rival regions with naturally abundant rainfall couldn't match. The terraces also prevented soil erosion, a critical factor in steep mountain environments where a single rainstorm can wash away unprotected soil. In 2026, these ancient systems are more relevant than ever. Modern water scarcity affects billions of people globally, and conventional irrigation methods are often wasteful and unsustainable. Engineers and agricultural specialists are now studying Andean hydraulic techniques for solutions to contemporary problems. In Peru and Bolivia, communities are reactivating ancient canal systems that were abandoned during colonial periods. When they restore these systems using traditional construction methods, they often function more reliably than modern concrete channels, which crack and fail under the same seismic and thermal stress that ancient stone systems withstand effortlessly. The environmental lesson is profound. These civilizations didn't just adapt to their harsh environment, they fundamentally transformed it through engineering mastery. They turned environmental limitations into advantages, using gravity as their power source, stone as their construction material, and physics as their design principle. No fuel was needed, no electrical pumps required. The system was entirely sustainable, powered only by the natural water cycle and carefully calculated structural mechanics. This wasn't primitive survival. This was sophisticated environmental engineering that modern sustainable development initiatives are only now beginning to appreciate. The ancient Andeans prove that technological sophistication isn't measured by materials used, but by the intelligence applied to solving environmental challenges. Their legacy, still flowing through stone channels after centuries, demonstrates that the most durable technologies are often the simplest in execution, but the most brilliant in conception.